So let's start out with just a little bit on Endress+Hauser. There's my my background information, contact information is right there, so you can see that. I'm located right here in Western New York, and I'd like to start out with this slide. Just a couple of brief comments on Endress+Hauser. Those are our shareholders. Endress+Hauser is a family-owned company. And I guess the biggest benefit, there's lots of cliches about working for a family-owned company. The biggest benefit to you as end users are about 7.5% of Endress+Hauser's revenue is devoted to push back into research and development, continuously introducing new products. And we're going to talk about 4 of those today in the world of flow measurement, but that's one of the nice things about a family-owned company is they direct where the money goes. So some facts and figures: 2.8 in net sales, 2.8 billion in net sales, and that is global workforce of 14,000 people, and there's the 7.5% reinvested into R&D, and that's that's on average every year, some years more, some years less. Some of the key industries, and they're really not in any order: food and beverage, water, wastewater, chemical, life sciences, oil and gas, primaries and metal, power. And what Endress+Hauser does is manufactures process measurement instrumentation and some associated products and services along those lines. We manufacture level controls, level measurement instruments, flow instruments, pressure, analytical, temperature products. You may be surprised. You may be buying other temperature products, and the temperature transmitters may be made by Endress+Hauser. We do system products, data managers, etc., and different types of software solutions depending on the project. This past year, and some of you all vote on these over the years, Control Reader's Choice Awards. So 33 total awards this year. 6 first place awards, and first or second in 22 of the 33 awards that are given. And you can see in second place there quite a few flow meter options. In fact, 5 of the 6 technologies that Endress manufacturers were in second place. So there's quite a bit of recognition globally and in North America for Endress+Hauser and the instrumentation they manufacture. Just a real quick history, started about 1953. And 1957, the first patent was filed. Endress+Hauser started as a level company. Their first patent was for capacitance level measurement. You can see a very early vibronic switch, which they invented and introduced in 1968. On up to 1986, the first straight-through Coriolis meter. 2005, we introduced our pH sensors with MemoSense technology, and that's extended through the better part of the analytical family. And heartbeat technology, we'll talk a little bit about that, and a lot of our flow and level instrumentation, introduced in 2014. In the US, they actually moved into the US in 1970, started out in Massachusetts, and in 1974, moved to Greenwood, Indiana, which is just outside Indianapolis, and built the campus there, and started in that one small building. And today, that's where it is, 500,000 square foot campus. There's 450 employees that work there in Greenwood, and 900 employees direct for Endress+Hauser across the US. The purple circle there is the new flow building. That's where all the flow meters are manufactured, tested. Our NIST calibration laboratory is in there. The green building is the green circle is the pressure level manufacturing. The The newest building is the red circle. That's temperature and recording. And the customer support center is actually in the blue circle. So that's where our process training unit is. Our process training unit is a complete facility, four big tanks. All the instrumentation that E&H manufactures is there, and all supported and run by a Rockwell Plant PAX. As you may know, we're an alliance partner with Rockwell. So you can actually use that facility for training on instrumentation and Rockwell products, and do a lot of live things right there. That's where we have a lot of training courses for instrument techs. And we also have those process training units throughout the United States. There's about 10 or 12 of them located in different areas of the United States. We will eventually have one in the Albany area. I'd like to just wrap up the overview of Endress+Hauser with this slide. Endress+Hauser uses representatives in the United States, and most of these representatives are fairly big representatives. You may recall, I've been doing this for 32 years as a representative, and years ago there could be 40 or 50 representatives covering the United States, and today we're down to about 15. And the reason for that is we make an investment in Endress+Hauser, and they make an investment in us. We send our engineers there for training. You may actually pick up the phone and talk to a tech that is actually employed by one of the representatives. So we share people, we share engineers, and we have a very large investment in what we do for E&H, and they have a very large investment in us. We're all trained. Obviously, we have to be trained in multiple disciplines, but we are all factory trained people that work as representatives for Endress+Hauser. You can see Trinova covering New York and New England, but also very large in the South. That's where Trinova actually started. They've been a representative down there for E&H for about 20 years. Trinova in the Northeast now since January 1st of 18. So we're into our third year. So Trinova is actually headquartered in Mobile, Alabama. So we're here today to talk about flow. And I'm not really going to get into a lot of detail on the different technologies and how they work and why they work. So if somebody wants more detail, just please reach out to me. We have almost all of these meters have different videos on YouTube that show how they work, why they work, show the technologies. Many of them are based on science from scientists from many years ago. They've been around for quite some time and refined. So of the flow meter types that are out there, there's probably 9 common types. There's always some offshoots, but there's 9 common types. Endress+Hauser actually offers 6 of these types: differential pressure, magnetic flow meters, vortex shedding meters, thermal mass, Coriolis mass meters, and ultrasonic meters. So in liquid flow, we offer 5 potential technologies: Coriolis, mag meters. Ultrasonics are limited to clean liquids. Typically, we manufacture a transit time ultrasonic meter. Vortex shedding meters, DP meters. Endress+Hauser does not manufacture the primary flow elements. Most of the representatives have relationships with other manufacturers. We have a relationship with Wyatt Engineering for orifice and Venturi meters. We have other relationships for pitot tubes, so we can still provide the complete solution. And then on the gas side, of course, Coriolis meters, ultrasonic meters. We have for gas. We're going to talk about a brand new one today a little bit. Thermal mass meters for clean gas. Vortex shedding meters for gases and steam. And differential flow meters, again, can handle dry gases and steam. So you have to find a flow meter. So the very first step is determining, what type of measurement technology is the best. So there's different requirements that kind of help you steer towards the correct technology, the best technology for your application. Not in any particular order. What type of accuracy do you expect? What type of pressure loss will the meter create, and what can you live with? What's your required turn down? So how high do you need to read, and how low do you need to read within a certain accuracy? We're going to talk a little bit about this with one of the other meters. If you need mass flow, do you want to do it directly, or can you calculate it? What's your installation situation? And this can be multifaceted. If it's a pipe, what's your line size? Is it an 18-inch pipe, or is it a 2-inch pipe? Is it, do you have straight run? Do you have valves and pumps in the line that you have to be aware of? Other installations like temperature probes, pressure probes, etc. And when we talk about etc., there's lots of etc. So when you talk to your sales engineer, your application engineer about selecting a flow meter, it's stressful, because the first thing he's going to do or she's going to do is come back and ask you lots of questions, because we need to look at many things to pick up the best fit. Some of these we talked about, but other considerations: the viscosity of the liquid. Is it corrosive? Is it abrasive? Again, what's your pressure loss? What kind of piping? What's your required accuracy? What do you need for turn down? What's the flow profile going to look like? What's the temperature? Many of the meters are limited in temperature to, 200-300 degrees on up to 800 degrees. So we need to know those types of things. What's the homogeneous of the liquid? Is it got air entrained? Is it conductive? And of course, a lot of times it boils down to price. We all want the world, and then when the sales engineer tells you what the price is, we sometimes back off a little bit and say, okay, what else can we do? So we can help with all those types of things. And when we talk about all these things, we really even haven't talked about the transmitter. What do you need for outputs? What kind of power do you have? What's the area classification? Is it a hazardous area? Do you have 4-wire power? Do you need to stay with a 2-wire device? So there's even more questions after that. So it is a little bit involved. Sometimes we leave instrumentation for the last thing. I'll throw something in there. But when it comes right down to it, if you want to make the best fit, we have to do a little discussion leading up to it. So if we look at the applications that are out there, about 80% of all liquids are conductive. So that's a good thing, because magnetic flow meters can fill that void nicely. There's non-conductive liquids such as oils and hydrocarbons, DI water, liquefied gases. On the gas side, there's clean gases, inert gases, there's natural gas, there's wet, dirty gases like a biogas, gases coming off a digester. Obviously, there's steam, both saturated and superheated, that we need to measure. And then there's plenty of special applications. Is it abrasive? Do we have to charge for it? Are we charging another part of the plant? Are we charging an end user? So do we have to know whether the meter is custody transfer rated? Do we need to measure from outside the pipe? Maybe it's a big pipe, 48 inches, and it's going to cost you an arm and a leg to have somebody cut it and install a meter. Can we measure from outside? Bidirectional flow. Do we need to measure in both directions? So we take all these meters and we can kind of put it into a chart and look at some of our solutions that we have out there to offer. Under conductive liquids, you can see a mag meter really exists in this world. Conductive liquids only, has some limits on temperature, but really has unlimited size ability. We manufacture magnetic flow meters from a 1/12 of an inch on up to over 100 inches. I think 108 right now is the biggest one that we've made. So mag meters can fill a nice niche, especially if it's a big line, which most big lines are conductive. It's wastewater, but it's obviously got to be a liquid. Ultrasonic meters today actually move into the gas area as well, but they can measure both conductive and non-conductive liquids. And they really go to the full line size because we have clamp-on technology. We can go outside the pipe or even drill through the pipe with a hot tap and insert the sensors right inside the pipe. So ultrasonic meters are a good solution. They tend to be for clean liquids. We call them clean, but they can actually have up to 5% solids. So sludges will work with transit time ultrasonic meters. Vortex meters fill a nice niche across all categories. They can actually go up fairly high temperature, about 800 degrees, so they can handle a lot of superheated steam. They're meant for gases and steam, typically clean. They can handle non-conductive liquids, so vortex meters a nice choice in DI water, areas like that. And they can obviously handle conductive liquids. What they can't handle is high viscosity. And we talk about high viscosity in turndown. Even viscosities of 5 centipoise or greater will start to affect the vortex meter's lower flow capabilities, low range capabilities. But generally anything over 20 centipoise, we will not even consider a vortex meter. Coriolis meters, again, liquid and gas and steam, a little bit limited on temperature. So it can't take the high temperature steam, but Coriolis meters will work in all types of liquids and gas. Obviously, there's limits on size. Anybody that's priced up a 16-inch meter knows that they can get pretty expensive pretty quickly. Thermal mass meters, again, typically right here in clean gas, they can, because we can do insertion, they can handle some pretty big line sizes and duct sizes. And lastly, differential pressure really can be used in any area. Depends a little bit on the nature of how dirty the liquid is, but we can do differential pressure meters on slurries. You just have to take care with the, obviously the differential pressure transmitter selection and the connection to the meter itself. So again, mag meters, conductive liquids, gotta have some conductivity, typically above 5 to 20 microsiemens, which tap water usually starts about 35 or 40 and goes up depending on where you're living and where you're getting your water from. They are a volumetric meter. Coriolis meters, good with all fluids. You have to be a little bit careful with air entrainment. And but they are mass meters, and they are multivariable meters. They'll give you density, temperature, and viscosity. Vortex meters, again, are volumetric meters, clean liquids and gases. They will do saturated steam. Today we have introduced, actually within the last year or two, pressure compensation as well, so we can do superheated steam and actual gas density calculations within the vortex meter. So you can get a true mass output for superheated steam and gases as well with pressure compensation. Ultrasonic meters, typically again clean liquids, some solid content. They are volumetric meters, and today we can do gas flow with ultrasonic meters as well. Thermal mass meters, all gases. In the case of Endress+Hauser, we do not do a thermal mass for liquids at all. It's all types of gases. We can do mixtures with certain meters. You do have to be careful with moisture in your gas. They will affect a thermal mass meter as far as the output, but the output is a true mass reading, and you can output temperature as well. And again, differential pressure can be typically applied to most any application. Obviously, there's limits on rangeability and some things like that that you need to be aware of. So I really want to talk about 4 innovative things that Endress+Hauser has introduced over the last couple of years, and one that's actually not even introduced yet will actually be released next month, but it's pretty much ready to go. So when we talk about Coriolis meters, Endress+Hauser has perhaps the most complete family of meters out there. A lot of people don't know this, but we make Coriolis meters as small as a 24th of an inch and as large as 16 inches. We make meters that go on filling machines that are small. You'll see them all over. So operating conditions, usually limited by temperature at the high end of about 400 degrees and about 5,800 PSIG. But Coriolis meters have a wide rangeability. They have an extremely high accuracy and repeatability, and they are multi-output. So when we talk about Coriolis meters, keep in mind that the measurement of mass flow and density is independent. So you've got 2 variables coming out of there. Most Coriolis meters are temperature compensated, so you can also get temperature as an output. And with a straight through Coriolis meter, you can actually measure viscosity. And that's internally within meter. That's, without separate pressure sensors, et cetera. That's all within the meter. So they are truly a multivariable meter, and both density and mass flow are independent of one another. So why would you even consider a Coriolis? You know that they're expensive. They are the most expensive type of meter to manufacture, and obviously cost-wise to you. So, but if you look at the cost of your product, so a 2-inch line with a typical flow rate of 50 gallons a minute, and that fluid costs $2.40 a gallon, that ends up being about $48 million worth of product at the end of a 40-week year, 40 weeks of running on a 24/7 type operation, $48 million. So if you improve that product control by just 0.1%, that's $48,000 a year of potential savings. And a Coriolis meter, it's always going to depend on materials of construction, but the return on investment for a 2-inch meter, could come in at around 3 months. So you can see that it's worth it in many cases to make that initial investment. And even if your product costs $1 a gallon, 80 cents a gallon, you're still getting a real good return on investment from a Coriolis meter. Plus, you always get the additional process variables, the temperature, the density, and potentially even the viscosity if you need it. So the meter we introduced about 2 years ago now is a little bit new design for us. It's a little bit more of a true YouTube design, and it is a multi-frequency type Coriolis meter. We call it the Q meter. Some of you have heard me talk about it, and it really makes improvements in some key areas. And I'm not going to talk about all of these in the interest of time, just I think 3 of them. But the key improvements have come in density, in what we'll call usable turndown, pressure drop, entrained gas handling, process sensitivity, repeatability, the size and the weight of the meter, and the safety features of the meter. Okay. When we talk about density and the density accuracy numbers that we issue to the general users, Endress+Hauser is an extremely conservative company. Being a family-owned company, that's, I guess, one of the traits is conservative nature. So all of our meters today have a reference accuracy and a usable accuracy in the field, or a projected usable accuracy in the field. And this particular meter, the Promag Q, is actually 50 times better as an end user accuracy in the field than some of the other meters we issue today. And then even if you took one of our standard meters and did a special density calibration, it would still be 5 times better. And that's the density accuracy out of the box. So basically 0.0002. Most of you take density and you convert it to some percent concentration. If you're looking at density, you're looking at a concentration of something, or maybe it's an evaporation process and you're using that density number to tell you how efficient your evaporator is running, make sure you're delivering the product that you said you're going to deliver. So the out of the box density accuracy of this meter is 0.0002 versus the out of the box density accuracy of some of our other meters is 0.02. Okay, the reference accuracy of those meters, if we were to have that meter on the lab, would be 0.0001. But when we take it in the field, you're going to mount it right after a pump, right after a control valve. It's going to be vibrating. There's going to be lots of things going on that don't go on the test stand. So your accuracy of your instrumentation has to be able to absorb some of those field situations, and the actual accuracy that's delivered is not as good as the reference accuracy that you can achieve on the bench. But the Promag Q is a guaranteed 0.0002 field accuracy. So you don't have to do a field density calibration, and it's not even recommended. And we don't even offer a special density calibration for this meter. And we don't just say it, we've actually proved it. Again, Endress+Hauser being a conservative company, most of our statements that we make are proven by a third party. So in this case, H&D Fitzgerald verified everything that we're telling you in the specification. So they tested the Promag Q on fluids of varying densities and viscosities, and it was able to hold its stated accuracy. So in all cases, when you buy a flow meter from Endress+Hauser, you're going to get a flow accuracy statement or a flow accuracy chart and a density accuracy chart on a Coriolis meter. The usable, yep.
Where you've got about 15 or so minutes left, okay?
I can't really hear you. Is this Steve?
be aware, you got roughly 15 minutes left, okay?
Okay. Okay, I saved the hardest one for last, so it's if I don't get to it, that's fine. But I want to talk about usable turndown. And that's basically in a Coriolis meter, you know you're going to get some pressure drop. We rate the meter to 0.1% accuracy of reading. So what's that usable turndown between a 14.5 pound drop to where we no longer can achieve 0.1% mass flow accuracy? We call that usable turndown. So the QMass meter has a 48-to-1 usable turndown. So from a 14.5 pound drop to where you'll no longer achieve 0.1% accuracy is 48-to-1 on a 1-inch meter, a little bit less on a 2 and a 3, 43-to-1 on a 4-inch meter. Okay, and those other numbers there are some of our competitors. So you can see that the Promag Q just leaps and bounds ahead of some of the other competition out there as far as usable turndown. Now that doesn't mean the meter goes to zero beyond that. I mean, the meters themselves can turn down extensively, 100-to-1 or more, but your accuracy will start to trail off on mass flow. Remember, a Coriolis meter measures density independently. So density, it does not care about the flow rate at all. As long as the meter is full, it doesn't have to be flowing and you'll get an accurate density reading. Okay, flow still tends to be velocity dependent, and your accuracy will start to drop off at extremely low flow rates. The third thing I want to talk about with the Q meter is entrained air. There's all types of entrained air. You see in the picture here, that's 15% gas void fraction. So that's 15% entrained air. And it occurs in all different shapes and forms. Some nicely mixed, some in slugs, others forming at the top of a pipe. So the meter is not going to handle these types of situations the same. It's all going to be different. And it's really tough to tell people, what's going to be your accuracy, because that question always comes up. So we can't really oversimplify this. Entrained gas varies because of velocity, viscosity, bubble size, the distribution, the pressure and temperature, the mounting orientation. But the Q meter is developed to handle entrained gas very well. So if we take a look at some applications, produced water, gas void fraction of 3%, the meter handles that with error less than 0.3%. These are actual cases. Milk delivery has entrained air of actually up to 10% because of the pumps and the connections, etc. We can achieve less than 1% accuracy on individual runs, 0.3% over 12 batches. Ice cream, they actually inject air or gas to lighten it up, to fluff it up. Very difficult to measure. So that's up to 30%. So we're better than 1% accuracy on density for ice cream. Same with cream cheese and even liquefied gases, liquefied nitrogen. So an extremely good result with the Q meter on entrained gas applications. And how do we do it? It's really a multi-frequency technology. So I'm not going to get into too much detail, but basically we're driving the tubes and measuring 2 different frequencies. So you can kind of see the different frequencies that we measure, and that's how we pick up and give us the improved accuracy on density and also handle the entrained air. So straight run. And as you get bigger and bigger meters, you don't always have the straight run. We get called into many situations where somebody says, I want to measure flow here, and there's absolutely no straight run of pipe. So it happens very, very frequently when you're discharging wastewater. The systems weren't necessarily designed to do flow measurement. So Endress+Hauser developed a magnetic flow meter that is a full bore meter that requires 0 straight run. So today, the only meter that really requires 0 straight run before this one is a Coriolis meter, but you're not going to put a 12-inch Coriolis meter on a wastewater line. So typically with straight run with magnetic flow meters, we wanted 5 diameters upstream and 2 diameters downstream at least. So you can see what happens to the flow profile after an elbow, and this is in all situations, not just water. So if you had a 10-inch meter, you need about 6 feet of pipe. 24-inch needs 16 feet of pipe. 48-inch meter needs 32 feet of piping to meet the accuracy specification. And if you had a real big application, I don't know if there's any water, wastewater people on, 72-inch meter needs 48 feet, and a 108-inch meter needs 72 feet of straight run to get the accuracy specification. So we developed a meter, and it is a full bore meter that requires 0 diameters of piping. So you can couple this meter directly to an elbow. And the way we've done it is we've done a multiple electrode design in combination with the electronics that sense the flow. So in the smaller meters, you're going to see 4 electrodes, and you can see in the picture on the larger meter, 3-inch and above, there's going to be 6 electrodes, 3 on each side. Okay. And those are the sensing electrodes. You see the electrode down at the bottom, that's still that's the ground electrode. And then there's actually an electrode at the top of the meter, which serves as your empty pipe detection electrode. So now you can put that meter virtually anywhere. Obviously the meter still has to be full. So you want it, if you're going to put it in a vertical, you want to try to put it in a vertical upflow. But you can couple that meter directly to an elbow and still achieve 0.5% of rate reading, which typically in the water wastewater world is more than enough. Okay, some different applications showing upstream disturbances, Ys and elbows, different thicknesses of pipe. So now this meter, and it really is not cost-wise, it's a couple $100 more than a standard meter. So again, this was third-party certified, verified, this time by TUV, which is a European testing laboratory. So we maintain that 0.5% accuracy coupled directly to elbows. Third technology that we're making a new introduction. This one actually was introduced next month, but we're already talking about it because it's pretty far down the line. Thermal mass meters. Endress+Hauser has been manufacturing thermal mass for many years now, over 100,000 in the field. So they're typically used in clean gas applications, a lot of utility applications, variable temperatures, bidirectional flow, that type of thing. So we've made some improvements to our current, and we've moved to the 300, 500 transmitter series. So we offer inline insertion versions. There's 22 now configurable gases in what's called the gas engine, and that's typically all the gases that are stored in the meter. We've introduced a new sensor, a new patented drift-free sensor. And we have automatic device verification. That's part of the heartbeat technology. And it improves the accuracy of the meter overall, about plus or minus 1%, 0.25% repeatability. So if you looked at thermal mass meters, it's a meter that is within the market specifications. It's also SIL compliant, SIL 2 compliant. And all of our meters have an onboard web server for configuration. So you don't need a Hart handheld. You just pretty much can plug into the meter and the onboard web server will open up. So the accuracy, again, the gas engine, 21 pure gases. You can take a look at some of those. IP68 NEMA 6P conforms to NACE if needed. We offer the heartbeat verification, which we haven't talked too much about, but is a program that resides within the meter that allows you to test the meter internally to make sure it's still operating within the specifications it was when it left the factory. We can do bi-directional flow with this meter. So that's the sensor design. If you buy the inline or buy the inline version, flow conditioners are built in. The sensor's removable, so if you need to send it back for calibration, you can leave the body in line and just send back the sensor. It's some nice features. And there's the drift-free sensor. Remember, a thermal mass meter is basically measuring temperature. So your RTDs can get, they can wear out, they can get moisture causes drift, etc. The temperature expansion and contraction can cause the RTDs to fail. So we've developed a drift-free sensor, and that it's a dry sensor. So it really limits the expansion and contraction of the sensor due to the temperature changes. And of course, it has heartbeat verification, which, as I said, it's basically a built-in program for monitoring the accuracy in the condition, the life of the meter, how it's aging. So heartbeat also can be, we can set outputs, and so you can actually tell if your gas is wet. You can tell if there's pulsations. Some nice features with heartbeat, and that's actually in all of our flow meters now. So, okay.
5 minutes left, okay?
Okay. And then the last technology, we talked about ultrasonics a little bit and transit time. Transit time technology has been introduced to gas, and we've just recently introduced a new gas flow meter that uses ultrasonic technology. So basically with transit time, pulses are emitted in the opposite directions. And then in the absence of flow or at zero flow, the upstream and downstream transit times are equal. As soon as you start to flow, okay, the difference in the transit time between the upstream and the downstream is directly proportional to the flow velocity. And of course, we know the area of the pipe of the meter, so we can compute volume flow. So these particular meters are used, you know, in gas transmission, flares, other types of processed gases where you need, you know, accuracy. Biogas, for example, which is typically a hot, wet, dirty gas. Thermal mass does not hold up well. Ultrasonic meters hold up very well in wet, dirty gases. So we do have some limitations. Pure hydrogen and pure helium cannot be measured with ultrasonic. They just don't exhibit the correct sound velocity profile. But basically, the new meter, line size is 1 to 12 inch, pressure ratings up to class 600, extreme accuracy 0.5%, higher temperatures up to 302 degrees. It's titanium sensors. The body itself is stainless steel, so we do have some limitations on corrosive gases like chlorines, but it's very robust against condensate, and it does have integrated pressure and temperature measurement. So we can do, you know, compensation, and of course it offers heartbeat technology. So some different meters now for gas gas flow applications. So the ProSonic B200 is actually the meter we use for biogas. That's a 2-wire meter that actually offers methane content output as well. And then the ProSonic Flow G300, 500 is all stainless steel titanium sensors and higher pressures. So some of the gases we can't do, you can see chlorine, fluorine, ammonia because of the corrosive hydrochloric acid gas we can't do. We're just not compatible chemically. And then the sound velocity is out of range in hydrogen, helium, xenon, but most other gases or a lot of mixtures we can measure with ultrasonic meters. Just shows you a little bit about how that sound transmission works and the inside of what the meter actually looks like with the transducers, pressure and temperature sensors. And of course, comes with a calibration certificate, like I mentioned, and a little bit on the heartbeat technology. The heartbeat technology does check all the sensors, not just the transit time. It will check the pressure and temperature as well, and output any type of alarms, etc., that you need to know if something's going wrong. And I think that's about it, Steve.
All right. Okay, Jeff. Yeah, thanks so much. At this point, you can take your mute off your phones. If you've got any questions, you can, let Jeff know. I didn't see any questions in the chat. Let me just check this to make sure. Yeah, I'm sorry, we do have a question from Jeff Scott. Do you have any thermal flow meters that have integrated temperature measurement, Jeff?
Yeah, the thermal mass principle is temperature. Okay, it's actually temperature sensors in there. And yes, you can output, besides flow, you can also output process temperature. So you can output the gas temperature. If I'm answering the question, you can output the gas temperature as well as the flow. The meters have multiple outputs.
Great, thanks, Jeff.
Any more questions? All right. Well, I guess that brings our meeting to a conclusion. I'd like to thank everybody for participating in the call today. I know we're all quite busy, especially in these challenging times. I'll send out the presentation that Jeff did later today, so you'll have a copy of it for reference. Again, thank you, and see you.
Thanks, everybody.
Thank you. Very
Thanks,
well
Jeff.
done.
Yeah, very nice.
Very interesting.
Really
Hey, Jeff.
good.
Jeff, it's Tom Gilmartin over here at Chorus. Any chance of getting professional development hours for this?
No, not for this.
Okay.
Yeah, we do have other online training where that can actually take place, though. But no, we didn't set it up for this.
That's fine. So Steve Fry, anytime you can get PDH, you're gonna draw me in every time.
Yeah, I keep in mind, Tom.
All right, cool. Thanks, guys. Have a good day.
Thanks.
Thanks all.